So, Objective BCR 4.2 is all about understanding half-lives by analyzing data to determine that value of a half-life, and understanding half-life values are used in radioactive dating, so to determine how old things are. Now, half-lives are just a way to look at radioactive decay. So radioactive decay is a natural process where unstable nuclei, and we talked more about that in 4.1, are going to break down because their strong force is weaker than their electromagnetic force. And when that happens, they decay into more stable atoms. And during that time, there's a amount of time that each element or each isotope takes in order to for that entire sample to diminish by half. So if we're looking at here, we have new elements being formed, but what's happening is they're becoming more and more stable as they go. And during this radioactive decay, just we talked about in 4.1, radiation is being emitted and we have new elements being formed because that nucleus is decomposing. Now, a half-life is, like, the definition for those people who want a firm definition is the amount of time it takes for the amount of a radioactive sample to decay by half into more stable atoms. So it is not for one atom to decay by half, it is for the sample to decay by half. So let's just say here we have a sample of 100 atoms. Okay, so it would be one half-life for that 100 atoms to become 50 of the stay 50 of the original, and then 50 of a non-radioactive nuclei. And again, it still could be radioactive. It's just not as unstable as what it previously was. So when it does turn into another atom, it just is not as unstable as the previous one. Or it could be completely stable, which can happen as well. Then we go through two half-lives. So if we go back to the number, we started with 100, then we have 50, and then we have 25 radioactive atoms. Okay, so those 25 radioactive atoms, we're reducing by 50% or half each time. So the most of my sample, 3/4 of my sample, is actually the non-radioactive nuclei. And then once again, we go through another half-life. And because we were at 25, this is about 12 or 13. You can't have a half of a radioactive atom. Like, it's either radioactive or not. It's either unstable or not. It's either one thing or another. Obviously, half of 25 is 12 and a half, but in theoretical, that works. But in actuality, you can't have half of an atom. So at this point, let's just say we had 12. So if we have 12 atoms left over after 3 half-lives, the remainder would be our stable nuclei. So each time in this amount of time is the same thing. So let's just say this was 1 year. Well, after another year, this would be 2 years, and then it would be 3 years. Okay, same thing with, let's just say this is 3 minutes. This would be 6 minutes. This would be 9 minutes. Okay, so the increment of time, even though that the amount is lower, it doesn't matter. Always by half. That is a constant variable of time. Now, just to reiterate that, half-lives for each isotope, no matter how big the sample is going to decay by half in the same amount of time. So, for example, here's a couple of them. Polonium-214, its half-life is 160 microseconds. That means if I have 1,000,000 atoms, it is to get to decay by half, it's 160 microseconds. If I have 10 of those atoms, same thing, to decay by half, it's 160 microseconds. It doesn't matter your sample size. Lead-214, 27 years, bismuth-210, 5 days. Now, I will never make you memorize any of this stuff. It's just to give you examples of how all half-lives are based on increments of time. And that amount of time is how much it takes for it to decay by half. So again, here you can see another visual. We have 0 half-lives, nothing is decayed. After 1 half-life, then half of it has decayed, and 2 half-lives, Then after that, it would be 75% has decayed. And it just continues to go by half and half each time. So reading half-life graphs and charts, I don't have any examples of charts here, but you can see that in the application. Graphs, they're all these exponential curves, and you will need to be able to read, okay, so right here, if I have 100%, in order to find a half-life, I have to go to 50%, and that would tell me, oh, it is 1 year is a half-life here. Well, here I'm given the amount of atoms. So here, if I have 1,000, to get to a half-life, I need to go to 500. And when I go there, I come down, which is about, I don't know, that's kind of hard to see, but I would say that's about 0.75. I would say 0.75 hours. Okay, so it's not quite right in the middle, but right around there. And kind of seeing the difference there. Okay, so all of those graphs are going to look the same. You just need to be able to read them. So just to reiterate the objective, understand half-lives by analyzing data to determine the value of a half-life, and then understanding half-life values are used in radioactive dating. And this last part is going to be something that you will see in the application questions. So determine how long ago something was decayed or something died is used in that radioactive dating because of half-lives. So if you guys have any questions, just let me know. Again, this is highly application, so making sure you don't only know the definition, but able to read charts, graphs, and analyze data is going to be important. All right, good luck.